Okay, now we're given numbers that are in scientific notation, and we need to take them out of scientific notation just to practice going back and forth. So I'm looking at like Earth's population. This was from the, I forgot what it's called, but it's kind of like a daily clock that if you set it to population, it actually keeps track of logged birth and death rates, and the number fluctuates instantaneously. So I just picked the number that I saw when I looked it up and exited out before it changed. But it is still approximately this value. At least down here is where it's changing. It's really not changing, you know, that 7.4 that we're going to see here in just a second. Okay, so if we're looking at the Earth's population, 7.39662 times 10 to the 9. And it's not a population unless you're talking about something. So there's that many people that make up Earth's population. Okay. So what this is telling me is I need to take this number, 7.396682, and multiply it by 10 9 times. Okay. If I multiply it by 10 one time, it goes there, 2 times, 3 times, 4 times, 5 times, 6 times. Oops, I need 3 more spots. 1, 2, 3. That means I'm going to need 3 placeholders where I have those to put my decimal place where I want it. So, all right. So now I've got 7396682 with 3 placeholders, 1, 2, 3, and it's still that many people. Okay, let's go ahead and put in some commas so we can talk about this as a number that, in the terms that we like. So we know we've got hundreds, thousands, millions, billions, and that for, you know, like, since that's like 396 million right there, whatever, that's about 0.4 billion. So a lot of the times people round this up to say 7.4 billion people. And billion is just times 10 to the 9 anyways. So if you get more familiar with your exponents and knowing that billion is 9 times, or, you know, 10 times 9, or 10 times 10, 9 times, excuse me. You know, million is times 10 to the 6. You'll kind of understand those order of magnitudes a lot better, but that comes with practice. Okay, let's look at part B, where we're looking at now. So this is a bunch of people on a big old flying rock in space, and now we're going to look at the distance between the proton and electron of a hydrogen atom. So we went from a really big scale, we're going to look at a really, really, really tiny scale. Okay, and the distance actually, if we were to draw the Bohr model, you've got hydrogen's proton here in the middle, and it's got one little electron on the outside. Okay, and so if we're going to look at this distance here, it's 5.2 times 10 to the negative 11 meters. Okay, so I'm going to 5.2 times 10 to the negative 11 meters. And remember that negative 11 means that I'm going to move my decimal place to the left because I'm going to be dividing by 10 each of those times. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I'm running out of spots. 11. And throw a decimal place down here. So I'm going to write this a little bit clearer. I'm going to go ahead and throw where I want my coefficient to be. Okay. Or excuse me, this is my coefficient. I'm going backwards. So where my decimal place is going to be. And that means I'm going to have to put 10 zeros before the 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then that 5. So now that's been 11 decimal movements, and then add that 2 there. And it's still meters. So it's a very, very, very small number, and it makes sense because it's a very, very, very tiny distance that we're measuring. Now if you want to throw a 0 in front, that's not going to change the way that this number is written. So either way, whatever floats your boat.